In this video, I'm going to discuss about supervised learning. And in the videos of next lecture in the next week, we're going to talk about unsupervised learning. As you may already know, the difference between supervised learning and unsupervised learning is on the type of the data that they're dealing with. When we're discussing supervised learning, we basically have a data set with labels, whereas when we are talking about unsupervised learning, we are not having the data set with labels. The data that are coming to us are without any kind of labels. And the whole idea in supervised learning is that we are given an input sample X and an output sample Y, where this Y's could be seen as our labels. And these together are work in a sense that there is a function f on the input set X that produces the output set Y. And in a supervised learning approach, we would like to learn the function f and then later evaluate it on new type of data. Generally, we have two types of supervised learning approaches. One is classification and the other one is regression. And the difference between classification and regression is the type of output value that they're trying to predict. When we have an output value which is an output set which is discrete, basically is categorical, it is 1, 2, 3, 4, or cat, dog, we're going to use classification. Whereas when we are predicting a continuous variable, for example the temperature or the grade of a student, then we're going to use regression. There are several types of questions that we could ask when we are having a set of labeled data and we want to do supervised learning. And here are some of them. For example, we are given a set of images and we want to, or the machine wants to be able to predict whether this is an image of a cat, image of a dog, car, or a house. Or, for example, we are given the characteristics of several different restaurants and the machine should be able to predict the user score that that restaurant has achieved. Or we want to know whether an email that we received is spam or not. So these are type of the questions, and many more actually, that we could answer by supervised learning. There are also several different techniques that are in the family of supervised learning, and I'm not going to cover all of them, but I'm going to briefly go over a few of them that are most popular and are used widely. You could look for the other approaches online or have a bit of research yourself. The ones that we're going to cover briefly in this lecture are, first of all, linear regression, logistic regression, and KNN or K-nearest neighbors. We are also going to discuss the approaches support vector machines, naive Bayes, and random forest. Some of these methods are using for classification, some of them are used for regression, and some actually could be used both on a classification problem and on a regression problem. Probably the most common method, or let's say one of the most basic ones, is the linear regression. And this is where we want to find the best line, and by that this is a linear function y equal f of x, to explain the data. As you can see in this figure, we have several dots, and when we are drawing the line that could to some extent explain the relationship between x and y. In this picture, at least, the assumption is that y is equal a of x plus b. And the most common method for fitting a regression line is the method of least squares. And in this method, we calculate the best fitting line for the observed data by minimizing the sum of the squares of the vertical derivation from each data point to line. This is like what you're seeing in this picture, that this is what we are doing. We are calculating the squares of the vertical derivation from a given point, and then we try to minimize the sum of all these squares. So if we achieve a line that the sum of all these squares is minimal, then we would say that is the best line that we have got. And because the derivations are first square, then there are no cancellations between positive and negative rules. So by that, basically what I mean is that it doesn't matter if the point is under the line or above the line. These are all squared, so they can't cancel each other. So in that sense, the error is quite meaningful. After a regression line has been computed for a group of data, a point which lies far from the line, as you can see, for example, here and here, and thus has a large residual value, is known as an outlier. Such points could represent erroneous data or may indicate a poorly fitting regression line. And if a point lies far from the other data in the horizontal direction, it's known as an influential observation. If there are a few of such points when we are having a data set, and we could even visualize it without defining our linear regression model, we could simply remove them from our data set, so we could have a model with a better fit. But if there are too many of them, either we need to deal with them in some way, or we need to look for another approach rather than a linear regression, because generally speaking, linear regression is somewhat optimistic, and it is not that realistic to assume that all our data points could more or less lie on a single line. I mean, of course, it's very much dependent on the problem that we are having in hand, but when we're talking about complex relationships, then linear regression probably is not what we need to have in mind. Once a regression model has been fit to a group of data, examination of the residuals, and that is basically the deviations from the fitted line to observed value, allows us as the modeler to investigate the validity of our assumption that whether a linear relationship exists or not. Plotting the residual on the y-axis, again the explanatory variable on the x-axis, reveals any possible nonlinear relationship among the variables, or might alert us as the modeler to investigate lurking variables. So let's go to another type of supervised learning approach, and this time we're going to talk about a classifier. And simply put, a classifier is a machine learning model that is used to discriminate different objects based on a certain feature. And the first method that we're going to have a look at is naive Bayes, and as an example you see that our classifier has divided the data points quite clean between three different categories or three different classes. So what is the naive Bayes? Let's assume that D is the data that we're dealing with and E is some sort of event. Then we use basically naive Bayes is going to give you the probability of a data point belonging to one certain class. So if we consider P of E as our prior probability, which is what we know or what we think we know about an event E with no other evidence, then P probability of D, considering that E happens, is the conditional, this one, is the conditional probability of D given that E happen or just the likelihood of D. And this can often be measured or computed precisely. It follows basically from the model assumption. So basically this is what we have. And P of D is the posterior probability of E given D, and it is the answer we are looking for, or the way we choose a best answer. And you can see the posterior probability is heavily relies on the prior probability of both the event happening and the conditional probability. Let me explain this with an example so you could get a better intuition on what we're talking about. Considering the problem of playing golf and the data is represented as you see here, we classify whether the day is suitable for playing golf given the features of the day, and the features of the day are outlook, temperature, humidity, windy, and then the answer we have is whether to play golf or not. The columns represent these features, and the rows represent individual entries. If, for example, we take the first row of the dataset, we can observe that it is not suitable for playing golf, as you can see here. It is a rainy day, hot weather, humidity is high, but there is no wind. We can make two assumptions here. One, as stated, is that we consider that these predicators are independent. That is, if the temperature is hot, it doesn't necessarily mean that the humidity is high. Another assumption that we can make is that all predicators have equal effect on the input. That is, the day being windy does not have more importance in deciding to play golf than, for example, the temperature being hot. And according to this, we can basically rewrite our bias theorem, and the variable y, the variable d is the class variable, which represents if it is suitable to play golf or not given the condition. The other way around. The event that we are interested in is the playing golf, and D is basically our conditions. And then we want to know under what condition the probability of playing golf is high. So simply put, this is how the naive bias look like. What is the probability of an event happening given certain conditions? I have already shown you one sort of classifier, and the question when we are dealing with a classifier is that how to evaluate it. We are interested at least in at least two different performance measures. The first one is the precision, which you can see here. Precision basically means within a given set of positively labeled results, what are the true positives? What is the fraction of true positives? And let me give you an example, for example, from the medical field. Let's say we have a model that predicts whether a patient that comes to visit us has cancer or not. And then true positive means that the patient has cancer and the model predicted correctly. False positive is that the patient doesn't have cancer and the model has predicted the patient has cancer. False negative basically means that the patient is cancerous, but our models say that the patient does not have cancer. And true negative is basically that the patient is healthy and the model predicts the healthy. And precision is basically the number of times that the model correctly identifies a cancerous patient to the number of all patients that have used the model. Recall, on the other hand, is defined as given a set of positively labeled results, then the fraction of all positives that were retrieved is called recall, and this is what you see in this formula. And the simplest measure to get the performance of a model is basically the fractions of all items that are correctly classified to the whole number of classifications. Basically, the number of the sum of all true positives and all true negatives over whatever that we have predicted is showing the accuracy. A way of checking whether our model is performing well enough is basically using cross-validation. Cross-validation is a useful method, especially when we don't have that much large data set. So if our data set is small and we want to still get a meaningful result, cross-validation is a good way to go with. And cross-validation basically involves partitioning the data in distinct training and test subsets, but several times. For example, here, as you can see, the original data set has been divided into 5 different sections, and in each section we're kind of moving this test data set forward. First, in the first try, the first portion of the data set is considered as a test data set. The rest of the data is used as a training data set. In the second one, the second portion is used as a test dataset, and the rest is used as a training dataset, and so on. And then we calculate error for each of these steps, and the final error, basically the mean error of all these errors that we have here. And one thing that you should keep in mind is that, as you saw in this example, our test set is never used to train the model. So the test is separated from the training data set, and then we use a test to evaluate the model. The naive Bayes model has some pros and cons. First of all, it is simple and fast. By that, I mean that it depends only on term frequency data for classes, one shot, no iteration. It's also very well behaved numerically. Term weight depends only on frequency of that term, decoupled from other terms. And naive Bayes can work very well when we have a sparse data, and this is a very good feature because generally in machine learning it's difficult to deal with the sparse data. So naive Bayes is one of the approaches that works pretty well on the sparse data. And it is where the combination of dependent terms are quite rare. But there are some cons with naive Bayes as well. For example, it is subject to error and bias when term probabilities are not independent. It's also not very good in modeling the patterns in the data, and one of the other downfalls is that it's typically not as accurate as the other methods. So it needs to be used with cautious, and it needs to be tested against the other possible approaches. Next, I'm going to talk about logistic regression approach. So far, we made a distinction between regression, which is predicting a real value, and classification, predicting a discrete value. The interesting thing about logistic regression, from its name, it's a regression approach, but in fact, logistic regression is designed as a binary classifier. It basically outputs 0 or 1. But why is it called regression? Because, as a matter of fact, what logistic regression predicts is the probability that the input instance is in the 1 class or it is in the 0 class. So in a sense, it's predicting a continuous value, which is a probability, but then that continuous value is translated to a discrete value, and thus it could be used as a classifier. So basically, it is a binary classifier, and it has the form, if you can see here, this is basically how the probability is calculated, and x is the vector of the features. What logistic regression is that this logistic function maps any value on this real line to a probability in the range of 0 and 1, and then based on that we could identify to what class our data point belongs. Similar to naive Bayes, logistic regression has some pros and cons. First of all, logistic regression is probably the most widely used general-purpose classifier, and in many research you could see that logistic regression is used as a base model. So base model is basically what you evaluate the performance of the other models against. So normally they run this logistic regression first step, and then whatever model that they're building, they compare the performance with logistic regression. Logistic regressions are also very scalable and richer feature space could be used, and it and can be trained very fast. It is used, for example, for spam filtering, new message classification, website classification, product classification, or most classification with large sparse feature sets. But it is not all good and rosy. There is this problem of overfitting. Logistic regression models tend to overfit on very sparse data, and one thing that you should know is that logistic regression is actually a generalization of naive Bayes approach, but only with some binary features. So basically, logistic regression can model a naive Bayes class. Another modeling approach that we're going to go briefly over here is the support vector machines. And a support vector machine is a classifier that tries to maximize the margin between the training data and the classification boundaries. You can see it here. And this is one of the very popular approaches for classification. And the idea basically is to maximize maximizing the margin that maximizes the chance that classification will be correct on new data. And the assumption here is that the new data of each class is near the training data of that type. Support vector machine is also one of the approaches, as I said, that is widely adopted and used. Another machine learning approach, supervised learning approach, is KNearest Neighbor, and or in short KNN. And the KNN algorithms assumes that similar things exist in close proximity. In other words, similar things are near to each other. There's this famous saying that birds of a feather flock together. So basically, this is the logic behind K-nearest neighbor or KNN model. This is an example of a KNN model, and as you see in this image, most of the time similar data points are close to each other. So these are basically more or less these blue circles, these red circles, the squares are close to each other. So similar data points, as I said, are close to each other. And the KNN algorithm hinges on this assumption being true enough for the algorithm to be useful. So the KNN captures the idea of similarity. Sometimes it's called distance, sometimes it's called proximity, sometimes it's called closeness. Basically the main idea is based on calculating the distance between points on a graph. You have seen it probably in your high school mathematics. There are other ways of calculating the distance, and one way might be preferable depending on the problem you're solving to the other one. However, the straight line distance, also called Euclidean distance, which is we have seen in our basic mathematics, is a popular and familiar choice. There are several aspects of KNN. First of all, the data is the model, so no training is needed. Basically, the model goes immediately to the data, calculate the distances. The new data is going to sit closest to the data that is similar to it. Accuracy generally improves with more data. The more data we have, the better we can decide where to put the new data point. And matching is quite simple and fast. We usually need data in memory, but this could be an issue that we could run out of disk. It also requires minimal configuration. Only parameter that is important is k, and this is what is deciding on the number of neighbors. There are also two other choices that are important to us, which first of all is weighting of the neighbors, that is the inverse distance and similarity matrix. What is it that we call two data points similar to each other, how we are defining them. So these were, in short, the definition of KNN and the aspects that we need to be aware when we are discussing them. KNN is a simple non-parametric algorithm, and what is interesting about KNN is that it could be used both for classification and regression. When we are talking about KNN classification, basically an object is classified by a major vote of its k-nearest neighbors in the feature space. And when we are talking about KNN regression, an object's value is assigned with the average of the value of its k-nearest neighbor. So basically the classification is the number of votes, and the regression is average value of the points that are close to our data set. Now we're getting to the random forest, and this is one of, let's say, better classifiers existing out there, quite useful. And the truth is that data science provides many different classification algorithms, as you have already seen some of them: logistic regression, support vector machine, naive Bayes classifier, and also decision tree that we haven't discussed there, but I'm going to briefly talk about them because they're very closely related to the random forests. But near the top of the classifier hierarchy is the random forest classifier. Of course, we also have a random forest regressor, but in this lecture, we are only looking at the random forest classifiers. So before getting to the random forest classifiers, let's go quickly over decision trees, as they are the building blocks of the random forest model. And it's probably much easier to understand how a decision tree works through an example. So imagine that our dataset consists of a number at the top of the figure. To the left, we have 2 ones and 5 zeros, and 1 and zeros are classes. And we want to separate the classes using their features. And the features are the colors, red versus blue, and also whether the observation is underlined or not. So how can we do that? Color seems like a pretty obvious feature to split by, as all but one of the zeros are blue, so we can use the question, is it red, to split the first node. So if it is red, we go to left. If it is right, we go to right. Observation, basically, that meet the criteria go down, yes branch. If not, they go to the no branch. The no branch, the blues, is all zeros now. So we are done there. We don't need to do more classification. Now we could use our second feature and ask, is it underlined, to make a second split. So the two ones that we have are underlined go down to the yes sub-branch, and the zero that is not underlined goes down to the right sub-branch, and then we are all done. Our decision tree basically was able to use two different features to split up the data perfectly. Let's put it like this. If the data is red and it is underlined, it is 1. If the data is red and it is not underlined, it is 0. If the data is not red, it is 0. So this is, as you see, quite simple to comprehend. Basically, decision trees gives us a set of rules to decide on the class of the given input. I say it once again. For example, I can ask, if I have an input that is red and it's underlined, it is 1. If I have an input that is not underlined, it is 0. And if I have a blue input, that is 0 as well. So random forest, like its name implies, consists of a large number of individual decision trees that operate as an ensemble. Each individual tree in the random forest spits out a class prediction, and the class with the most votes becomes our model prediction. So basically, in this example, we have n different trees, and each of them predicts something. Then we see what is the majority vote, and then we go by that majority vote. In this example, of course, we don't see what is happening here, but if we assume the proportion continues, that always it predicts class B more than class A, then we are going to predict the class of that input to be B. The fundamental concept behind random forest is a simple but powerful one, and that is the wisdom of crowds, a majority vote in a sense. The reason that the random forest model works so well is, first of all, a large number of relatively uncorrelated models that are our different decision trees here operate more or less as a committee that will outperform any of individual constituent models. As a whole, they are working better than one. Basically, it is this famous saying that the wisdom of many is better always than the wisdom of one. And the low correlation between models is the key, just like how investment with low correlation, like stock and bonds, come together to form a portfolio that is greater than the sum of its parts. Uncorrelated models can produce ensemble predictions that are more accurate than any of the individual predictions. And the reason for this effect is that the trees protect each other from their individual errors. So basically, if one single tree make a mistake in predicting a class, or a few of them make mistakes, then the other tree predictions would cover for them. In another word, while some trees may be wrong, many other trees will be right. So as a group, the trees are able to move in the correct direction. And this is the beauty of random forests. They basically allow for making mistakes. Some trees make mistakes, some of them are, the majority are not going to make mistakes, and as a whole, we are going to get a more accurate result, and this is the superiority of random forests to many other classifiers out there. So what's happening next? You now have the basic theoretical ground of some of the supervised learning algorithm existing there. You have an idea what classifier to use on one sort of problems, what sort of regression methods you can use. Now in the next video I'm going to briefly show you examples of these 6 different supervised learning approaches that we used here. We're going to see an example of linear regression, logistic regression, naive bias, support vector machine, random forest, and naive bias. Good luck and see you in next video.